Hey guys, welcome to CakeWalk Cambridge. I'm Aisha, and you're watching the paper 6 of Specimen 2023. So I was studying for my A2 Bio Planning Evaluation Analysis paper, which is tomorrow, and I saw this comment on my YouTube channel that asked to explain the paper 6 Specimen paper of 2023 for 0610 IG Bio. So I thought I'd do it in my break. And yeah, so let's get into it and not waste any time. I will only be attempting the first 33 marks. The last 7 marks is drawing, and that's pretty self-explanatory. And it's all written very well in the mark scheme, like the guidelines of how to draw. So I will not be attempting that. But let's get started. Okay, so question one. Catalase is an enzyme found in plant and animal cells. It catalyzes the breakdown of hydrogen peroxide to form water and oxygen. Here they've given you the chemical equation, and you know that the enzyme that works on this equation is catalase. The oxygen produced forms a foam because the oxygen that is produced is basically gas. So when the gas is produced, it settles above the liquid mixture and it forms a sort of foam that you can probably see when you perform these experiments in labs. So you can measure the height of the foam to determine catalase activity, obviously, because if the catalase has a high activity, that means it catalyzes the reaction to have a high reaction rate, oxygen will be produced faster in a specific amount of time, and so more oxygen. So if you have um, catalase that has a slow activity versus catalase that has fast activity, um, the catalase that has fast activity in, let's say, 5 minutes will produce this much oxygen, and catalase which has slow activity in the same 5 minutes will produce less oxygen because the rate of reaction is slower. So you can measure the height of the foam to determine how fast catalase is working in a set period of time. Okay. So a student investigated catalase activity in cooked and uncooked potato tissue. So when you're looking at activity of an enzyme, you have to correlate this to the rate of reaction. Whatever you've learned in that chapter or whatever you know of that chapter, you correlate it to that. Okay? That is the factors that affect rate of reaction. That's temperature, surface area, pH, enzyme activity. So all of these will now come like, they're going to form like a jigsaw puzzle and come together. Okay, so now these steps are really important. So the student first cut two potato cylinders that they were identical in size and shape. Okay. They put 5 centimeter cube of 3% hydrogen peroxide solution into one test tube and labeled it cooked potato. So they've not put anything in this test tube yet except the hydrogen peroxide, but they've labeled it cooked potato because that cylinder, one cylinder that's going to have cooked potato. So the potato cylinder that's cooked will be transferred into this test tube. And in another test tube, they've put the same 5 centimeter cube 3% hydrogen peroxide solution and labeled it uncooked potato because the other potato cylinder that is not cooked will then be transferred into this cylinder. So you can differentiate. Already here you can see they've standardized the volume of H2O2 solution as well as the concentration given by 3%. Okay, and then after that we put one of the potato cylinders into a beaker of hot water for 5 minutes. Now this step is to cook one of the cylinders. So when you're putting the cylinder into hot water, as you've seen your parents do when they cook, it's cooking the potato. Okay. Then you remove the potato cylinder from hot water and you put it into the test tube labeled cooked potato. Okay. So the potato, so what you've done is you have two potato cylinders. Okay. You have two test tubes, each that contain the same volume and concentration of H2O2. One test tube is labeled cooked potato, the other test tube is labeled uncooked potato. You've cooked one of your cylinders and you transfer them into the cooked potatoes test tube, which has 5 centimeter cube, 3% H2O2. And then you transfer the other uncooked potato. You touch it, you don't treat it at all. You put the uncooked potato cylinder into the other test tube labeled uncooked potato, which also has 5 centimeter cube, 3% hydrogen peroxide solution. Okay. Then you leave the potato cylinders in these hydrogen peroxide suspensions for about 3 minutes. That's again another thing they've standardized. Both of the test tubes are left for 3 minutes, and after 3 minutes, you measure the height of the foam produced in each test tube. Okay, I hope this is clear. Already we can see they've standardized volume of hydrogen peroxide, concentration of hydrogen peroxide, and the time frame. Okay, that we're leaving the potato cylinders inside. So this is what it looks like after 3 minutes. So the uncooked potato has this much foam, and the cooked potato has this much foam. As I told you earlier, the foam is going to form a layer above the liquid solution mixture, okay? Because the foam is basically bubbles of oxygen gas that are collecting at the top, and they form foam. You can see there's a ruler in between these to measure the height of the foam, okay? This is what it looks like. You look, the height of the foam is going to be measured for the uncooked potato from here to about here, right at the top. Okay, and for the cooked potato, it will be from here to about here. And then you subtract the lower value from the higher value for each, and you get the height of the foam. Okay, and is there anything else that we can use from this? Yeah, that's it. As you can see now that the foam for the uncooked potato is much like greater in height than that for the cooked potato. Why? So when you're cooking the potato, when you cook a piece of potato in hot water, you are basically exposing the enzymes in the potato, specifically catalase, because we are only measuring the rate of catalase activity, to a much higher temperature than its optimum temperature. So what does this do? It denatures the enzyme. The enzyme no longer is able to function smoothly and properly. Enzyme substrate complexes cannot form, and because the active site of the enzyme changes shape, and so the rate of reaction decreases. Rate of reaction decreases, meaning less H2O2 is converted to H2O and O2. So that means less gaseous oxygen is released, which causes a smaller height of foam to form at the top of the liquid mixture. That's simply why the activity of uncooked potato, the activity of catalase in uncooked potato is much higher than cooked potato. Okay. Prepare a table to record your results. Now for this, what you had to do, so they've asked you to measure the height of the foam, and you record these measurements in your table. So this is pretty easy. It's a solid 3-mark question. So you make a nice table, use ruler and a pencil. And if you wanna put your data values in pen, that's fine. That's good. You make this kind of table. Okay. And here you will write like treatment of potato. I'm not going to write it because I can't write it with this thing, but you write treatment of potato. Okay, and you divide it into 2. So here you're going to have cooked and uncooked. Okay, write the ED as well. I'm just going to be lazy and leave that out. And over here you write mass of foam, sorry, mean height of, wait, no, it wasn't mean, just the height of foam, sorry. You write height of foam after 3 minutes. Okay, and you make a slash here. You always put units in your table. So you do a slash and you can put like millimeters or centimeters, whichever works. But make sure that you record your measurements in the height and the units specified at the top of your table. So let's just give it random values right now. I am not calculated. I'm on my laptop. I'm not done like the ruler measurement and everything. I'm just going to give random. So we know that the cooked was much less than uncooked. So let's say the uncooked was about 3 centimeters, so we can like 30 millimeters, and the cooked was about 1 centimeter, that's 10 millimeters. That's all you have to do. And remember, they need to be recorded to the same number of significant figures. So if you're doing one significant figure here, you will do one significant figure as well here. Okay, same if you're going to do decimals, like if supposing this was 1.3 centimeters, then, and if this was 2 centimeters, then you would have to do 2.0 centimeters to 1 decimal place. Okay. Okay, that's basically what you do for the table. Next, calculate the difference in height produced by the cooked and uncooked. Now, for this, you need to use your table values and this measurement. Subtract the lower one from the higher one, and you put it down with units, millimeters, centimeters, whatever. Okay, units have to be consistent in all your work. So, state one conclusion for these results. As we already concluded, the catalase in uncooked potato had a much higher activity than that of cooked potato. Okay, that's basically your conclusion. You can go on to explain it, but they've only used the command word state. So they don't require an explanation. So you can just leave it at that. Identify the independent variable in this investigation. So what we were investigating here is the effect of treatment on catalase activity. Okay, the effect of treatment of potatoes. So that's basically cooking or uncooking it. So catalase activity is affected by the treatment of potatoes, which means catalase activity is dependent on how the potatoes are treated. Therefore, the treatment of the potatoes will be the independent variable because they affect the outcome of the test. Okay, so the independent variable is going to be treatment of potatoes. State why it is important that the two potatoes are of the same surface area and same size and whatever. I don't remember the last part of the question. Were of the same size. It is because to ensure that they have the same surface area. Why? Because enzyme activity, rate of reaction, all of them, as I said, they're going to come together now. Enzyme activity, rate of reaction, they're dependent on surface area. So you have to ensure that the cooked and uncooked potato have the same surface area to ensure that the test is fair. Okay. So that's why the same size of potato cylinders is to ensure same surface area. Next, two other variables that were kept constant. So they've already said that one variable kept constant was the size and shape of the potato cylinder, which basically means that the surface area is kept constant. Now, two other variables, we discussed three. One was volume of H2O2, that was 5 centimeter cube. The second was concentration of H2O2, that's 3%. And the third was the time frame, that was 3 minutes. So you can add any of these two out of three and you're through. So variables that are kept constant are basically the variables that are standardized in the experiment. And these three were the standardized ones. Identify one possible source of error in this method. So when I went through this paper quickly before solving it, the one thing that came to mind was that if you notice the foam that formed over the liquid solution, it had an uneven base and top. So when you're measuring it with your ruler, you don't really know where to start from. As you saw, even I struggled to make that red line near the ruler on the third side or something. It's because the foam has an uneven like surface. Okay, the line is uneven, so it's basically so you may measure like less. You may measure less than what was actually there. Like you may measure a height smaller than what was actually produced of foam, or you may measure a height that was larger than what was actually produced. So that's an error. Another error I saw on the mark scheme was that the potato after being cooked was not dried. Okay, so it was wet when it was placed into to the other suspension, and you have to basically dry the potato. But the most obvious one that came to mind was that the foam above the solution, above the mixture, was not even. So it's difficult to measure because vision is subjective. Okay, next. This is my favorite. I love 6 markers. A student stated that catalase activity is same in all species of plants. Plan an investigation, 6 marks. Okay, first what we're going to do is identify the independent variable. So the independent variable is going to be species of plants. Why? Because here we're testing whether catalase activity is influenced by different species of plants, whether catalase activity is dependent on the species of plant. So therefore, species of plant becomes your independent variable and catalase activity becomes your dependent variable. So to to test your independent variable, you're gonna need variations of your independent variable to test in different species of plants, right? So the mark scheme says you need to use at least 2 species of plants. I always say go for 5. That's to be on the safe side. Even in A2 bio, I use 5, and that's always like what you do. So what you're first gonna do is you're gonna use 5 species of plants. Okay, so I'm just gonna write 5. Okay, I'm just gonna write the whole thing for you guys. My handwriting is not so bad in real life. Okay, so 5 species of plants. And then what we're going to do is we have to have some sort of controls, okay, some sort of standardized variables. So what we're going to do is we're going to ensure that we're going to test only the leaf from these 5 species of plants. So we'll test the same part. We're going to test same part of all species, which is the leaf. Okay. Next, what we're going to do is we're going to ensure that the plants are of the same area. The plants are taken from the same area. They are exposed to the same climatic conditions, same environmental conditions. The leaves that we take from the plant have the same surface area, the same. We can try and ensure that they have the same mass. Okay, those things are what we're going to standardize. We're also going to try and standardize the temperature by placing our setup in a thermostatically regulated water bath at around 30 degrees Celsius because that's when catalase works best. Okay, so again, so we're gonna keep the temperature common. And then we're going to keep different parts of the plant common. So not just like the age of the plant, surface area of the leaf, okay, all of that, okay, and then the place that the plant was, the species were procured from, okay, all of that. Then what we're going to do is we're going to add um, hydrogen peroxide solution to each of these leaves. So we're going to take one leaf from plants of 5 different species. We're going to place them in separate beakers. In every beaker, you will use the same volume and concentration stated earlier, so you don't get confused. 5 centimeter cube of 3% hydrogen peroxide solution. Okay, so we're going to have 5 setups. Um, so concentration and volume of H2O2 is also going to be same. Okay, all of this is going to be in a thermostatically regulated water bath. We're going to place the leaves, and then after that, we can either use the same method that they did to measure the rate of reaction, that is, measure the height of the form above, or you can put them in separate test tubes, these setups, attach each test tube to a delivery tube. I'm going to draw it up for you. There's a test tube, attach it to a delivery tube, which then is attached to a gas syringe. Really bad drawing. Okay, this is attached to a gas syringe. We place a rubber bunk to ensure no gas escapes. And all the oxygen that is formed in this mixture by the activity of catalase from the leaves on H2O2, that's the solution. The oxygen is going to travel via this delivery tube and give a reading on the gas syringe. So we're going to measure the volume of oxygen collected. So we can either do that, we can count the bubbles of oxygen that form in set time, or we can measure the height of foam in set time. Okay. So all of these three will fetch you 1 mark. Choose one. If you're not comfortable writing your own method and you're not familiar with the apparatus, mirror the one that they've given you already. Okay. So we find um, the volume of oxygen or whatever, and you divide it by your time period. Supposing you leave each setup for, let's say, 5 minutes, you divide each the volume of oxygen or number of bubbles counted or the height of foam by 5 minutes or 300 seconds, depending on which unit you want your thing in. Okay, and basically you repeat the experiment like 3 times, okay, for reliable results. If you want to give a risk assessment, you can say that hydrogen peroxide solution may not be, safe to deal with, so wear chemically resistant gloves. That's all right. And repeat, and you calculate averages for for reliable results. And of course, what else is left? You can draw bar charts for each species and the rate of reaction, okay, the rate of catalase activity, and then you can compare. That's pretty much, I think, all you have to do. I don't think I missed anything. And to know more about planning and investigation, you can check out my other video on the channel. That's ATP Planning and Experiment by CakeWalk. I think this is pretty much it. I don't have the mark scheme in front of me, but this is the answer that I gave when I answered it orally and then checked the mark scheme. So I think this is fine. You get 6 marks. So 1 mark for 5 species, 2 marks for control. So 1 mark for 5 species, 2 marks for control, 1 mark for a method of collection of whatever, 1 mark for repeats, 1 mark for risk assessment. That's 1, 2, 3, 4, 5, 6. Okay, you got 6 marks. That's pretty much it. And also adding hydrogen peroxide to the leaf gives you 1 mark as well. So you get like you've got more than enough points. Okay. Next. Potatoes contain starch. Starch can be broken down to give reducing sugars. So describe the test to identify starch. This you have to mug up. This is also on my biomolecules video. So the starch test is the starch iodine test. Iodine turns blue-black in color in the presence of starch. So that's what you'll write. Iodine, add iodine solution. It will turn blue-black in color in case of a positive result. And for reducing sugars, Benedict solution, you add Benedict solution, heat it to 80 degrees Celsius, and it will give a brick red color because of the brick red precipitate that forms, which will indicate a positive test for reducing sugars. This you just have to mug up, like the tests. There are just the 5 of them. They're very easy. Don't worry. Just go through my video if you are still confused. Next, question 2. Question 1 was that easy. Can you believe it? Okay, question 2. A woodlouse is a small animal. The rate of respiration of a woodlouse can be measured using a simple respirometer as shown in figure 2.1. As the woodlouse respires, the drop of colored liquid moves along the capillary tube. As you can see, at the start, the drop of liquid is here, and at the end, or after 30 minutes, the drop of liquid comes closer to the woodlouse. Why? I'll explain it to you. So when we respire, we breathe in oxygen and breathe out carbon dioxide. So here in the setup, we have potassium hydroxide, and potassium hydroxide absorbs carbon dioxide. So here, whatever the woodlouse breathes, whatever carbon dioxide the woodlouse breathes out is absorbed by potassium hydroxide. Okay, so that doesn't cause any change in the setup or anything. But whatever the and one second, if the carbon dioxide was being breathed out without potassium hydroxide, this drop of liquid would move away. But potassium hydroxide absorbs carbon dioxide to prevent the drop of liquid moving away. Okay. Now what happens is we breathe in oxygen. When we breathe in oxygen, when the woodlouse breathes in oxygen, it creates a kind of suction in this tube. Okay, because it's breathing oxygen, so that lowers the air pressure and it pulls the drop of liquid towards itself, which is why the drop of liquid moves towards the woodlouse. And because carbon dioxide is not being released, the otherwise, if there was no potassium hydroxide, the oxygen that we breathe in would kind of pull the drop of liquid towards the woodlouse, and then the carbon dioxide would just push it back. That would not cause net movement or anything, or like a significant change in movement. But because we have potassium hydroxide absorbing carbon dioxide, only sole action of breathing in is what causes the colored liquid to move towards the tube. Here we have a ruler to calculate how far along the tube it moves. Okay. Let's so I know the questions that come after this, so I'm just gonna use this. Okay. So here we can see the drop of colored liquid is at around 4.5 centimeters. Okay, it's right in the middle. You can use your ruler and check. And here it's around 0.5 centimeters. Okay, we're just gonna keep that in mind and move on. Here they said record the start position and the end position of the colored liquid in the capillary tube. We've already discussed 4.5 centimeters, but in millimeters. Units are important. Therefore, 4.5 into 10, 45, and 0.5 into 10, which is 5. Okay. Calculate the distance moved by the drop. You will simply subtract the lower from the higher height. That's basically 45 minus 5, which is 40 millimeters. Okay, and this is moved in 30 minutes. Now we need to calculate the rate of movement of the drop in millimeter per liquid. Whenever rate is given, you know that your denominator is going to have a unit of time. So the rate of movement in millimeter per minute, we know that the distance moved by the drop was 40 millimeters. So we have the numerator. And the time period was 30 minutes. So over 30 minutes, we already have the denominator. We just divide 40 by 30, you get 1.333. But here the question specifically says give your answer to one decimal place, which is why your answer is going to be 1.3 millimeters per minute. Um, the rate of movement of the drop of colored liquid along the respirometer can be used to estimate the rate of respiration. Correct. Because it's basically, this experiment basically is measuring the distance moved by the drop, which is brought about by volume of oxygen breathed in by the woodlouse divided by the time, okay, which is basically your respiration rate. So what they've done is they've investigated the respiration rate in 4 animal species A, B, C, and D. They've had 3 trials. Why do you have 3 repeats? To remove anomalies, identify anomalies for greater reliability, etc. So you have to calculate the missing mean for animal species A. Mean, as we know, you add all these values 1.5 plus 1.7 plus 1.3, divide them by 3. Your answer is going to be 1. Okay, that's all you have to do with an easy 1 mark. Plot the bar chart. Okay, now to show the mean rate of movement of the drops of colored liquid in the capillary tube of the 4 animal species. Now this is really important because you cannot have awkward scales. I've already done this counting before. So the x-axis has around 50 small blocks and the y-axis has around 60. If I'm not mistaken, I calculated roughly from my screen. So what we need to do is we have to draw a bar chart, which means there also has to be space between the bars. So it's gonna look like this. I'm just gonna draw it. 2, 3, 4. Now, one thing to remember is when you start, what I used to do, when you start your graph, you draw the x-axis and label it x, draw the y-axis, let it like the full line and let this label it y like that, but like right down to the bottom, the whole thing. Yeah. And over here on the y-axis, you will label mean rate of movement, okay? Mean rate of movement, and then you make a slash and you write the units, which is millimeter per minute, okay? And on your x-axis, you will write species of animals, and then you label each bar A, B, C, and D. Now, what's important is that there's always space between the bars of a bar chart, and the width of each bar has to be equal. Okay, that's very important. So what we know is that we have 50 blocks, okay, and we have 4 species. So that means 4 bars plus 1, 2, 3, 4, 5. 5 spaces in between. Okay, so what we can do is we can make sure that the width of each bar is around 5 blocks long. Okay, this is 5 blocks long, and that gives us 5 into 4, which is 20 blocks already used out of the 50. Okay, now the blocks in between also have to have equal spacing. Okay, so what we can do is the number of blocks remaining are 50 minus 20, which is equal to 30. Okay, 30 is divisible by 5 because we have 5 spaces, 1, 2, 3, 4, 5. So we divide it by 5 to see how thick each space will be, how wide each space will be, and that's 6 blocks. So you will have 6 blocks. After 6 blocks, you will start your first bar, which is 5 blocks wide. Then you'll have another 6 blocks, your second bar, which is 5 blocks wide, another 6 blocks, then your third bar, which is 5 blocks wide, and then your fourth. Okay, and then that's just how your x-axis is going to look. Okay. Now for your y-axis, you have 60 blocks, and your range, which is on the previous slide, goes from 0 to maximum, I think, 3 millimeter per minute. So what we can do is every 10 blocks can be 0.5 millimeter per minute. Okay. So we're going to divide it into 6 sections. So 60 by 10 blocks is 6 sections. Okay. So 1, 2, okay, this is a lot more than what I did. 3, 4, 5. Imagine these are 6 equal sections. I've not divided it correctly. So you'll have 0, you'll have 0 0.5, 1.0. Everything has to be to the same decimal place. Okay, so 0 0.0, 0 0.5, 1.0, 1.5, 2.0, 2.5, and 3.0. So your scale is not awkward because you have every 0.5 is 10 little blocks. And then you have to basically, you just calculate the scale, because once you have that, this is just easy. You multiply, you divide 0.5 by 10 to find out how much each block is worth, how much each block is. So how that works is 0.5 millimeter per minute is in 10 blocks. So one block is how much? 1 into 0.5 by 10. You calculate the significance of each block and you plot your graph. That's all it is. In show you use pencils, straight lines, sharpen pencils, draw your axis, label units, label your axis, all to one decimal place, equal spacing, same width. Okay, that's basically what you have to do. Now it says state the letter of the animal species which has the highest rate of respiration. That was in the table in the first part of the question, and that's C. Okay. You just have to look at which one had the highest mean rate, and that's easy. And then suggest a suitable control for this investigation. Now so now when you are describing a control for an investigation, basically you're planning an experiment to ensure that the rate of movement of the drop or the movement of the drop is solely caused by the animal species breathing in oxygen, respiring. It's solely caused by the animal species respiring. Okay. So now to test whether it's just the animal species respiring, you'll have a separate test tube which has the same setup, but instead of the animal, like the woodlouse or whatever it is, you will have inert material or dry beads or something, okay, beads or something, some material like that. And obviously that's not going to respire, that's not going to cause any movement, okay. And that's why it's a control, because it'll prove to other people that the movement of the drop is caused by the animal species and not by any other external factor, okay. So you're going to use inert material or beads. of the same mass as the animal species to standardize that. The student decided it would be better to calculate the rate of respiration per gram of animals so that the values could be compared. So now rate of respiration, as we already know, is millimeters per minute. But now they have said per gram, which means your new denominator, like another part of your denominator, is going to have gram. Okay, now what is gram suggest? Gram is a unit of mass. So to calculate the rate of respiration per gram of an animal, first what you're going to do is measure the mass of the animal using a balance. State the apparatus. Even if it's not required, state it. You never know when you need it. So you measure the mass of the animal using a balance, okay, and you measure it in grams, and then you divide the rate of respiration that you've already found out for each species by the mass. So you have the rate of respiration per gram. That's basically it. I hope you understood this, and I hope I explained it well. And I hope this helps you. If it did, please leave a comment, subscribe to my channel. And if you have any more questions, you can email me or comment, as you guys have already been doing. All the best for ATP. It's an easy paper, and I know you're gonna kill it. If you have any other doubts, let me know, and I will try responding as soon as I can. Tomorrow is my paper as well. And yeah, all the best. And thank you actually for requesting this video. I've never gotten down to do it otherwise. So thank you, all the best, and let's get through this together.